cryofusion? Is it cryofusion.org? Right?
Yeah, that's it.
Cryofusion.org, which also links to Jean-Paul-Biberian.net. Amazing former lead professor of physics, University of Marseille, sponsored our work with Elizabeth Rauscher and others here in France. Our hero. Thank you, Jean-Paul.
Well, thank you. Okay. I just came back from Fort Collins in Colorado. There was a conference, international conference on pulse fusion. Just ended Friday, so I'm just back.
Speak as loud as you can.
Okay.
Yeah,
I forgot there was no microphone here.
Oh, sorry. That's our apology.
Okay, anyway. So I was at this conference in Fort Collins, Colorado, and we had something like 150, 60 people there talking about cold fusion. And it was quite interesting because we are moving forward pretty well, you know. But maybe people are not familiar with what I'm talking about. So I will back up and tell you a little bit story about what's happened. Actually, on March 23, 1989, there was a press conference at the University of Utah where two scientists, one was Martin Fleischmann from the University of Southampton in England, and Stanley Pons from the University of Utah. They announced that they had made a fusion reaction in the test tube. Test tube, you know what a test tube is, it's not very big. Fusion is like a nuclear reaction. And obviously this is not possible. I mean, this is not possible to make fusion because maybe you're not familiar with nuclear science, but to fuse two nuclei, for instance, if you take two hydrogen ions, I mean, hydrogen is the smallest atom there is. So if you remove the electron, you have just the nucleus, and the nucleus is a plus charge. And we have plus and plus, they repulse. They don't want to get together. In order to get together, you have to push them. Just like magnets, when you play with magnets, you have seen that, they're opposite, if they are contrary, they will stick, and if they are opposite, they will repulse. And with charges, it's the same thing. So they have tendency to repulse. So in order to fuse them, you need to go to the high temperatures, because temperature means movement and kinetics and speed. So in the center of the sun, supposedly there is, I don't know, nobody put a thermometer in the center of the sun, so this is just calculation. So the idea is that there is 50 million degrees in the center of the sun, so the pressure, the speed, makes that they will fuse. In the H-bomb, that's what they do. The H-bomb is the fusion of hydrogen nuclei. And in order to get them to fuse, they have to use an A-bomb before to put the pressure. So there's two bombs actually in the H-bomb. There's first an A-bomb and then H-bomb. So it's complicated. And that's what they are trying to do in Cadarache in France, in the ITER project. They want to do the same thing by going to 150 million degrees to fuse them, because the pressure, the speed will be such that we end up just fusing. But in a test tube, you have at room temperature. Room temperature, nothing happens, like that. So these two scientists are not dumb, they know. I mean, they are highly educated. They are professors. They know what physics is. But they did the experiment. And the experiment was the following. They took a test tube, or more or less a regular test tube, put two electrodes. One was made of palladium. Palladium is a precious metal. Actually, when I married, I wanted to have a ring. I don't like rings really. But I went to this place and I saw this ring. It's palladium. They have rings in palladium. I want to have one. I have a palladium ring, 95% palladium. I think nobody buys palladium rings if they want to gold. I mean, palladium is twice as expensive as gold. Anyway, so there was one electrode made of palladium. The other one was platinum. And palladium has a tendency to absorb hydrogen very quickly, like a sponge, You put sponge in the water goes in, and you put hydrogen in palladium, it goes inside. It's amazing. So that's why they chose palladium. So there was water, not regular water, but heavy water. The one where you have to change hydrogen with deuterium. Deuterium is like hydrogen, but it's called an isotope. It has an extra neutron, so it's twice heavier. So what they did, they put a current and loaded the palladium with deuterium. And at one point, when there's a lot of them, they squeeze. I mean, the idea was, if I can squeeze them, between the atoms of palladium, Maybe at one point they refused. And that's what they did, and it worked. They got a lot of heat. They had more heat than they had electricity to get it to work. So that was more than necessary. So their idea was, it has to be nuclear. I mean, otherwise, how can you explain it? So there was a major press conference in 1989. I mean, all the media took over. Every scientist in the world who had access to palladium, platinum, and heavy water did the experiment. Most failed, as usual. I mean, I don't know if you have done experiments or you cook in your house, but even making pastas is not that simple. You have to go to Italy to get good pastas. Make coffee is difficult. I mean, it's difficult. You have to wait. Really, you know? I mean, who cooks here? I don't know, but cooking is difficult. And with cooking, you have a recipe book, you know, or you learn from your mother. Or father, maybe. These days you have to be careful. yeah, be careful. You say mother, that you are sex sensitive. You know? So, anyway, parents, they, whoever, teacher. So, if you learn from a book of someone, it's not easy. So, these people didn't have the correct recipe. They didn't know exactly what to do. They did something. Most failed, obviously. It was normal. And especially people are not that interested in spending too much time on something that fails. You know, you want to succeed because your career there, your business, I mean, whatever. A few people succeeded, but finally there was a report. I mean, it's a long story, complicated. Nobody wanted the thing to work anyway, so they killed the thing completely. And they didn't kill people, they killed the field by saying it was error, bad manipulation, bad work, a bad intention, whatever. I mean, sloppy work. So the whole field died, but underground, under the radar, people continued to work.
People like Jean Paul.
Me and others, you know. A few hundred people continued to work in the US, in Japan, Italy, different countries. People continued to work without not too much noise. There were regular meetings, you know. Every year we have a meeting like that, international meetings, plus local meetings also. And the field continued to develop, slowly, slowly, slowly. And there was a material problem. I mean, these electrodes, palladium electrodes, were actually something like 2 millimeters in diameter, 2 centimeters, 1 centimeter long electrodes, very small thing, palladium. But the quality of the palladium is not the same from one batch to the other. And even with the same batch, you have differences. So there was no reproducibility in the results. Sometimes it worked, sometimes it didn't work. And people didn't know why it was working and not working. So it's difficult because how can you know what's happening inside a piece of metal, you know? So for years, people have tried to improve and improve and improve and improve, but the success rate was not very high. Finally, people said, wait a minute. If we work with water, we are limited to 100 centigrade because it's not boiling. So if you want to go to higher temperature, you have to go under pressure. In the nuclear reactor, they go to very high pressure because otherwise water vapor at 100 centigrade will not give a lot of electricity, it will waste a lot. So you have to increase the temperature. But it's complicated, very difficult to do. And electrochemistry is complicated, you have to add water and things, I mean the electrode gets poisoned. Some people started trying working in gas phase, because in gas you can go to temperature you wish with gas. You can have very high temperature gas. Palladium is a metal that melts at 1,553 degrees. That means it can go to high temperatures. And maybe you're not familiar with Carnot cycle, but to make electricity out of heat, you need to go to high temperatures. If you work at low temperature, you don't get much yield. You will lose a lot. I mean, in the nuclear plant, if you want to have 1 gigawatt, you have to spend 3 gigawatts of heat. You know, 2 are going in the air, making clouds. To my children when they're young, I would tell them that this is the clouds factory. Because where the clouds come from? You can see them. And they believe me, you could see the clouds coming out of there. So they thought the clouds were made there. So because they waste 2/3 of the energy making clouds, you know, or heating the rivers, you know, or the ocean. Depends what you do. Anyway, now people have started working with gas. And not only gas, that's not enough. You need to have, if you put a stick of palladium in gas, it will not work well. But if you make powders, it's better. Because we know that the reactions are happening at the surface of the material, not in the bulk. So if you go to a large surface, you make powders, because powders have a lot of surface, little material. And at the end, if it is nano, there's almost only surface, there's no bulk at all. So recently, and under the, well, several people have tried, but there was an Italian scientist, Piantelli, who started working with nickel. I mean, I was telling you that palladium is twice more expensive than gold. And deuterium is a gas that you can buy. I mean, it's difficult to get. I mean, if you want to buy deuterium in France, you have difficulties, you know. I mean, first, we don't produce deuterium in France. It has to come from the US, all the way from the US. I don't know why we don't make them in France. There's no customer, I guess. And second, it's nuclear grade. I mean, supposedly you cannot touch, you cannot add it, you know. Even though deuterium there is in nature. But anyway, it's like that. And deuterium is expensive. 1 liter of heavy water costs about 400 euros, something like that, 300-400. Maybe if you buy by bulk, it will be cheaper. But it's quite expensive. And people try to work not with palladium and deuterium, but with nickel and hydrogen. Because of the work of Piantelli in Italy, it was proved that there was excessive with nickel and hydrogen.
And that would be related to Rossi's inspiration.
Rossi started with Piantelli's work.
Yeah, exactly.
But the problem I have with Rossi is that he never say anything about what he's doing. He's making demonstration, and scientists don't like demonstration. They want written papers where there's description of what they're doing. You know? Because I have seen, I was in a place one day, and there was this woman. She was cutting too, and then she was glued back. You know. Do we have a woman you want to try? I mean, we have a good soul.
That's the best analogy I've heard for a long time.
I mean, this is a video. This is a YouTube type stuff. You know, you can't believe it. You know, you don't know what they're doing. But scientists never do that. They don't like demonstration. They want a paper where they describe exactly what you do.
Physics, the meter, the measurement.
Yeah, you know, they're done exactly. Tell the recipe. So Rossi did things. He keeps on making demonstrations, but people don't believe demonstration. You know, how do you measure? Anyway, I don't want to go into that.
And Jean-Paul's expertise is the measurement.
I mean, in science, you work with measurements. No measurements, no science.
And they're hiring him to do that. They pay him to measure.
This is philosophy, you know. If you don't want to do that, then do philosophy. That's okay. No problem. I mean, you believe in God, you believe in God. You believe in this, you believe in this. You know, who cares? I mean, but science is measurements. No measurements, no science. You know, just something else. It's not bad. I cannot say it's bad. I've seen this woman cutting too. This is true. I've seen it. And she went back on afterwards. No blood, nothing. And I've seen this woman disappearing from the stage and back in the room, you know. I've seen that. And second later, she was there. Instantaneous. How can you do that? I don't know. Is that good? I mean, but it's not science. It's show. I mean, it's a different story. People are confused sometimes, you know. That's why there's so much confusion going on. Anyway, since we passed from liquid to water to gas, things are better. We get reproducibility now. I have myself experiments that show 100% reproducible, you know. The problem is not reproducibility anymore. The problem is getting to the industrial level. Because it's good to do science, but it's only science. I mean, you know that there was a Big Bang, but what else about your breakfast in the morning? Nothing. I mean, it doesn't change anything in your life. Even if you know the Big Bang was 13 billion years before, 14 billion years before, who cares? That doesn't change your life. It's just science. It's good, but it's science. Now, if you want to do something practical, you have to do more. So what happened, as I was telling, everybody was working under the radar, quietly. I mean, it's not even necessary to work under the radar. Nobody wanted to see you anyway. There was no radar to see you. There's no problem. There was no to see you. The idea was, okay, that thing doesn't exist. I was working in France, in Marseille, at the university, and every year I worked on cold fusion for 25 years. So, and after a while, we have every 4 years we have to write a report about the activities of the laboratory. So it's a big laboratory. So one day I said, well, I should write a page about what I'm doing on cold fusion. So I wrote this page. And then there were 15 people came to visit the lab, check out everything, what we're doing, And then the report came back, stop immediately this activity, it is not part of the research of the lab, I mean, something like that. So I was happy enough that to have, knowing the director of the lab who knew me, so he said, well, just do it, don't say you're doing it. That's how things work. You know, most of the time, you know.
The French government was absolutely opposed to fusion research.
Yeah,
The French government was making money selling nukes.
Nukes, yeah.
Yeah, it was pretty obvious.
And also, the thing is, you're not supposed to make nuclear reaction in your home, you know. This is reserved. This is reserved. This is reserved to the military and to the nuclear industry, not to the general public. I mean, imagine you're making neutrons in your house, you know. That's true. I mean, you're not supposed to do that. Imagine the day people become free, you know, what can they do? Nothing.
There we go.
They have to prevent to do things. No. Anyway, that's my philosophy. So we continued working for years and years, and there was a Japanese scientist just passed away 3 or 4 days ago. His name was Arata. Arata was a great scientist. He had a great idea. He decided to make, well, how do you, well, tell you something. If you make nanoparticles of metals, they're very small. If you put them together, if you heat it up slightly, they will fuse one to the other. They will fuse even at low temperature. Because there's always diffusion of atoms. You know, atoms don't stay still. You know, you think they're still. In the average, they are still, but they move all the time. So they diffuse. And at one time, if you leave them together, they will make a chunk of metal. You know, they will not stay as spiral. They will just fuse one to the other. So it's a problem. So you start with a nanoparticle, but you end up with a solid material. So the idea is to get them separate one from the other. How do you get them separate? So this guy had a great idea. He took an alloy of zirconium and palladium. Zirconium, okay, now to be more complicated again, you know maybe that there are two sides, there are crystals. You know crystals, right? I mean, everything, in metal, everything is crystals. I mean, atoms are all organized. They are not at random. And then there are glass. Glass is not organized. That's why it's expensive to buy a glass in glass and a glass in crystal, you know. That's that price. One is ordered, crystal, and you ring the bell, you know, and the other one is disordered. You cannot make a metal as a glass alone. You cannot. It doesn't work. It's impossible. But if you make alloys with two metals, and you freeze, when you melt it and you freeze it very quickly, they don't have time to reorganize. But you have to do it very quickly. So what he did, he mixed it zirconium and palladium. When he melts it at very high temperature and drops it on a wheel, water-cooled wheel, copper water-cooled wheel, and as the zirconium and the aluminum and the palladium alloy comes on the wheel, it freezes and it becomes disordered, amorphous material. Now, so you have a foil, a few micron thick, of this material, then you heat it in air, oxidize it. The zirconium gets oxidized, but not the palladium. And then you end up with small grains of palladium in a zirconium oxide matrix. So these grains of palladium now are separate. And they cannot fuse one to the other because they're separate, like in a cake, you know, when you get this.
A cake?
Yeah, it was great, it was, whatever, you know, could be anything separated by the cake. And he's done experiments with that, showing that when you put hydrogen, even at room temperature, you get excess heat. I mean, you put nothing, actually, just hydrogen, it heats up. You had to put high pressure, 100 atmosphere of pressure of hydrogen.
And then it would absorb the hydrogen.
It absorbs the hydrogen and it gets heat.
Yeah. I mean, Jean-Paul, not to interrupt, but I knew Jim Patterson before he made the first palladium beads for the first cold fusion experiment. And the reason they couldn't replicate is he couldn't make the cake again. He couldn't get those palladium beads baked correctly to separate the palladium. And when we first went to Jean-Paul's lab, Valerie showed it because we were talking about the fact that in occult chemistry, palladium is dodecaecosa, actually this outer valence symmetry, presumably, and this, in fact, felt cold in your hand. It was actually imposing with charge. So the geometry of palladium is part of the magic, that's all we're saying.
And first, you have to check nickel because nickel works also.
Oh, yes, I didn't.
You should have a look at nickel.
Yes.
I'll give you some homework.
Yes.
Okay, because nickel is much cheaper. I mean, nickel doesn't cost much, and it's almost zero. And hydrogen is really free.
Yeah, yes, hydrogen.
So
right.
nickel and hydrogen are good candidates. But Arata started with palladium. Recently, there was a major program in Spain where two Nissan cars, Nissan manufacturers, cars, Toyota also, and with another group, and 4 universities got together to make a project of making cold fusion using this kind of materials. So now they are progressing a lot, and now they're capable of having reliable excess heat every time it works, between 5 watts and 25 watts of excess heat continuously, just by heating it up. That's all they do.
Palladium.
No excitation, nothing.
Nickel or palladium?
Okay, what they use, it's a mix nickel and palladium, and with hydrogen, not deuterium.
Uh-huh.
And they say that if they use deuterium, they get about the same results. So it's not very sensitive to hydrogen or deuterium.
But if they could make the beads geometry better, maybe.
So they're trying to improve. They made different type of alloys. They have tried nickel and palladium. They have tried also nickel and copper. It seems that nickel copper works well also. So I have done this type of experiment, exact same experiment with a different type of calorimeter. I mean, measuring heat is not simple. I mean, it's not easy to measure heat. It's one of the most complicated things to do. Measure voltage is easy. Take a voltmeter and measure it. Measuring heat, there's not such an apparatus where you put it in the thing and you get the heat, There's nothing like that. You have to build it for your need, adapt it to your need. So I have developed a new calorimeter called a heat flow calorimeter because I measure the flow out. I mean, if you are in this room, for instance, you have walls. And depending on temperature here and temperature out, and depending on the size of the walls, you get loss of heat, That can be calculated. I mean, architects know that, It's not very accurate, but it's pretty good. But now we need something extremely accurate in our case, because we're measuring small amount of heat. So I've developed a calorimeter like that. The walls are not, instead of having one thermometer inside and one outside, there are many more inside, so that averages the measurements. So anyway, that works. And I've shown that I can get something like 7 watts at a temperature of 500 centigrade. 500 centigrade is a very good number. And it seems that going up linearly with temperature, pretty good. So if I go to 800, 900, we'll be better. So why is it working with nanoparticles without excitation? Because people thought, and it has been proved, that you need some kind of excitation. I mean, cold fusion is not something static. Otherwise, it would have been discovered a long time ago. That means just putting hydrogen in nickel will not do anything. If you put hydrogen in nickel or deuterium in palladium, you need to do something to it. You have to shake it somehow. You can shake it with light, you can shake it with pressure, with magnets, you can shake it with anything you want. You have to shake it. So then it will work. Because things
Shaken, not stirred.
What?
Shaken, not stirred.
So you shake it somehow. And then, but that's true for large crystals. Now if you go to nano, something else happens. You are in a quantum field now. Things are, if you are at, it's called the Bose-Einstein condensation. Maybe, I don't know if you heard about it. Anyway, it doesn't matter. If you didn't, I will explain it. That explains superconductivity. At one point, these atoms, if you have certain conditions, they start to behave collectively instead of being independent.
Bose-Einstein condensate.
Yeah, Bose-Einstein condensate. The atoms behave collectively. So if there are too many, it's impossible to do it. But there are a few, then they will do it. Have you ever looked at people walking in the street? 2 people. You see them, they're walking together. They're in sync. Even though they don't even touch each other. I always fun looking at people. Sometimes they're in phase, sometimes they're out of phase, but always in sync.
It's like women tend to synchronize their ovulation if they're living together.
No, they synchronize with the moon. It's even harder. The difference of the moon.
So what enables them to behave as a group?
So if you have small crystals, then the atoms, the hydrogen atoms that are inside, can behave collectively. And so they shake by themselves. There's no need to add some excitation. So it's why it's becoming interesting to work with nanomaterials, because no excitation is necessary. I have done some experiments with larger powders, and then I need an excitation to get results. But only if it is large. If it is small, you don't need that.
You have surface availability, the smaller it is.
So the smaller the better.
That's right.
That's what I say when I go to the airplane. I'm short. It's better than tall ones, you know. I mean, I see tall people, you know. It's hard for me. I wonder what it is for them. And they're a surfer, you know. And now they have this flight that lasts 17 hours flight. Can you imagine? 17 hours and you are 6 foot tall, you know. Forget it, you know. They should give those seats only to short people, you know. They should make a stop for the other ones.
Nanotech.
Nanotechnology. So nanotechnology is great. So we are improving now slowly, and we have reproducibility. There's this guy in America is with Aerospace Association. He has made his own powder. The thing is quite expensive because to have this film of zirconium, palladium, nickel alloys, he goes to the Ames laboratory. It's a military laboratory. It costs him $4,000 for 10 grams of material. So it's very expensive. You can make it yourself if you have the equipment. It's not too bad. So he has reproduced the same experiment. So we think that we are not far now from industrial applications. The Japanese groups are working intensively to move forward.
And that's automotive?
Yeah, it's for automotive. Yeah, I mean Nissan is making electric cars. Now, if you have a cold fusion generator, you have unlimited mileage for your car. You know, that would be much better than having to plug it somewhere. You know.
And John, a lot of our people are thinking about alchemy, of course, and we talk about isotope transition, non-sort of charge collapse. Do you want to sort of
yeah.
a metaphor?
I didn't tell you what the product of the reaction is. I mean, something's happening. We don't know what's happening exactly inside. We have measured, I don't mean me, I mean some other people, I measured production of helium-4, helium-3, a little bit of tritium, a little bit of neutrons, but very few, but mainly helium-4, which is the one you put in goes into sky balloons, you know.
Is that an example of transmutation?
Yeah, that's a transmutation because you have two deuterium atoms that fuse and make helium, you know, that's all. It's a transmutation.
What were the two atoms?
Deuterium.
Deuterium.
Deuterium, you fuse and make helium.
And it's relatively cold transmutation.
Yeah, it's cold. I mean, relative. I mean, cold and hot are related. You know, that's rich and poor. The same thing. You know, it's small and large. You never know what that means.
So you're doing a little alchemy over there.
No, we're doing alchemy. I mean, no doubt. Now, I have. When Stan Pons is one of the two discoverers of cold fusion. He lives in France, not too far from here, actually. I mean, well, Europe is small anyway. So, and one day he gave me all his equipment because he stopped working. And he gave me one of his electrodes that was 10 centimeter long, 2 millimeter diameter. He said that one gave a lot of heat. So that was in 2001, but when he gave me that. And it stayed in my drawer somewhere for years and years and years. And finally last year, I met someone who had the equipment to do some analysis. So I said, wow, that's a good chance for me to analyze this electrode. So, and I knew that some people said that there was silver produced out of palladium. If you know the table of elements, you know, next to palladium, you have silver. You should know that. I mean, I'm sure you all know that.
One small step for mankind.
one plus. Anyway, so I went to this machine. He has a special machine where you can etch the surface. So you have an oxygen beam actually that strikes the surface, etches the surface, and you have a mass spectrometer that can analyze what's coming out. So you can do both. You can do analyze it, and you can analyze the surface. Plus, as you etch it, you can make a depth profile, and you know how deep it goes. If you calibrate the system, you know exactly in microns what the depth is. So we analyzed it, and we found that there was. Okay, I'm sure you're familiar with isotopes. You know, all the atoms are not equal. There's some heavier than the other. So silver has two isotopes, 107 and 109. They are about 50-50. But when I did the analysis, I found some hot spots where 107 was 10 times 109, 10 times in large factor. So we did the profile, and what we saw that after 1 micron, it was normal. So for 1 micron, there was anomalies, you know. So just transmutation.
Surface effect.
Surface effect.
Yes.
But as I was telling you, it's better to use powders because you don't have only surface.
Surface effect again.
So, because, I mean, it makes sense, you know, everything comes from the outside, so it has to start with the surface, not from the inside.
So you made palladium to silver, was that?
But we make silver out of palladium, which
And
is
silver
about...
was coming up to the surface.
Well,
No, it's produced.
It happened at the
Produced
surface.
at the surface.
Okay,
that's what he
Produced
said.
at the surface, it's not made at the
So
surface.
that's
It's
alchemy
not
right there.
diffusing.
Yeah, but
Yes,
you
I can-
lose money on that reaction.
Yeah, you do a lot of money. It's not good. It's not good. It's not lead into gold. It's a gold into lead. You know, it's the opposite. It's not good at all. It's not business. It's not the right alchemy. You know, if you want to do alchemy, don't do that.
You'll get harder gold for that one.
And some of the people say you can transform nickel into copper. But copper is cheaper than nickel, so it's not good either, you know. It's good for science. I mean, science is one thing and business is another one. Just like arts, and who cares about arts? Expensive. So, so far our transmutations are not very cost effective, you know.
But it's fun.
But it's fun. No, one thing is, anyway, you're producing 107, different type of silver, not like the natural.
That's true. Yeah.
Actually, I will tell you a story.
Helium 4.
With some of my friends at the Cadarache, we were thinking maybe we should look at alchemy. Did they work or not? But the problem is that with gold, I mean, the alchemists are supposed to make gold, but gold has only one isotope, so you cannot separate alchemical gold from natural gold. There's only one. And actually, it's illegal to make alchemical gold. You know that.
Yes.
It's illegal. Yes.
In most of
Illegal.
history, it was illegal too. In the
Well,
Middle
really,
Ages.
Like legal by all
By law, by law.
Oh, by law.
Yeah,
There's a
well,
lot, yeah.
Not all over the world. There's certain countries who
No,
are
in France it's illegal. I don't know.
In the U.S., for sure, it's illegal.
Yeah,
I don't
there's
know.
other countries who
Oh, yeah.
It's illegal to make alchemical gold. Anyway,
Yeah.
so we couldn't analyze alchemical gold because we cannot know if it is natural or not. But apparently the alchemists made also silver. So silver has two isotopes, and we thought, oh, if we can find some alchemical silver, then we can see if it is natural or not. So we went through all the museums in Europe, and in France, the museum, what's the name of the museum? The famous museum in Paris. Le Louvre, okay, good. Le Louvre, everybody knows it. Le Louvre said, we cannot have alchemical coins since alchemy doesn't exist. That was a good point. Well, okay. That was natural, that was a good answer. Then we went to Nuremberg in Germany, and they had a collection of alchemical coins, gold and silver. Oh, we said we want only the silver one, we don't want the gold ones. So they said, what do we want to do with that? So we said, well, we want to analyze. So they wanted to make sure we're not going to destroy their coins. So we did some analysis with an electron microscope and a SIMS machine also to analyze the composition of some of the French 5 francs or something like that, silver coins.
Which they really believe was alchemical silver.
I mean, historically it has been done by alchemy, you know. I don't know if it was or not, they believe or not, it was historical. So they sent me 6 coins, beautiful coins, came by special packaging, you know, went to the airport to get it. It cost a lot of money to get that. It cost us 700 euros just to have a package like that from Nuremberg to Marseille. You know? Anyway, so we start analyzing them, first with the electron microscope, and out of the 6, 2 had a lot of mercury in it. So wow, that's great. One had 40% mercury, amazing, you know.
Oh.
40, yeah. It's a lot of mercury, you know. So what do you put mercury in coins, you know? Anyway, then we went to the other machine to analyze the isotopic composition. And there, to our great unsurprise, we're not very happy, it was natural composition.
Oh, so the mix of isotopes, but 107, 109?
It was the same, the natural ratio.
50,
So, but we don't know if alchemy makes abnormal silver or natural. You don't know that. We don't know even where it starts from, what they're doing to do that. Anyway, that was the end of it. We wrote a paper on that and published it.
But you know, when Dean Kelly, supposedly the British Royal Society, said it was the purest gold that had been measured to that point in history.
That's possible.
And that was,
But unfortunately, they have only one isotope. That's my problem.
Has any other natural silver ever been found with that content of mercury?
I doubt.
so there's
People
an
don't
indicator
look at
right
these
there.
things, you know. That's the problem. They don't look at it. I mean, most people don't think it's possible, but they don't look at it, you know. They think something doesn't exist and don't even check, you know.
Well, we're checking.
Well, there was January, I think, there's a journal in France called La Recherche, kind of scientific American style, and they wrote a short article about cold fusion saying that it doesn't exist and so on and so forth. So I wrote to the editor-in-chief. I said, well, it worked. We are working on it. I mean, there are things going on. If you want, you can come and visit my laboratory. I will show you an experiment that works. He never answered. What can I do? I mean, if people don't even want to look at it, there's nothing you can do. Forget it. You cannot do it. They don't want to come. What can I say? I cannot force them, you know. So that's the thing. So anyway, to make a long story short, we are moving forward to applications. Now, a lot of industry is interested. Yeah, you don't believe. Everybody is looking at the field. From NASA to oil industries, everybody is watching. They are ready to jump on it as soon as it starts, you know. Some are starting to invest. I mean, Bill Gates has put $6 million at the University of Texas to do research. So, and they have results. They don't tell what it is yet, but I know they have results. Industrial Heat is a US company who is funding research in cold fusion because they know that it will come out sooner or later. It will come out. So they're putting money now. It was for a long time there was no money at all. You know, it was really working on the shoestring. But these days things are changing a lot, and we're getting money to work because you need to buy equipment. It's expensive. I mean, all these things are very expensive. I buy 20 nanometers nickel powder from Germany. It costs me 300 euros to have 25 grams, you know. It's very expensive.
Speaking of industrial heat, though, would you like to comment that Bill Elizabeth contended that Rossi's error was not properly identifying his isotope sequences, and that's why he couldn't achieve regulation?
I don't know what happened. The story of Rossi is a big problem because he doesn't give the details of his work. So how can you analyze something if you don't have the details? So you have to believe what he said. So what he was doing, an experiment that was supposed to last 1 year in the U.S. for producing 1 megawatt of energy for 360 days, but according to the industrial heat, the measurements were wrong. It's possible. He's French. So we don't know what happened actually. I have no idea. I told you about, I've seen this woman cut in two, and so I don't know.
What would be the more complex chemical name for nickel? Is it, do you know that, or is it just nickel?
Nickel.
Nickel.
No, nickel.
Yeah, the elemental name.
What do you want to change the name? Some people are not happy with their name. They go to the government and it's complicated. In France, you can do it.
The compound
Just,
of nickel.
I think we're probably close to
No,
time.
we're
Okay.
okay.
Are we okay? Is you
Okay.
So you can keep. Do you want to summarize for 5 minutes, and then
Yeah.
we'll do some questions.
Okay, then we finish it up. So now we have moved from basic research to applications. We have moved from electrochemistry to gas phase experiments, which is much better. And I think we have, let's say, we have solved one problem, reproducibility. The second is getting excess heat, abnormal excess heat. Now what we have to get is abnormal excess heat by putting very little heat at the beginning. I mean, if you are putting 1,000 to get 1,001, it's not very worthwhile. If you are putting 1 and you get 1,000, it's much better. So that's the next step. And then the step afterwards is to go to kilowatts and megawatt, whatever. But in the watts range, we're already there. We want to go 1 order of magnitude higher. The Japanese program is to get 1 kilowatt in the next couple of years. So we are moving pretty fast. It's a question of materials. Find the right material. So a lot of testing has to be done because we have no clue what to do exactly. So making mixtures, alloys and stuff, and trying the conditions.
Because we
So
do
we're
believe
getting
that
there.
when Patterson failed to make the next palladium bead, which kind of crashed us all, that if he had understood conjugate fields to be centripetal to stabilize those more nano palladium, the conversation we could have.
Okay, so we don't know what about it. That's about it. I can answer questions if you have it. I don't know if you have a question. I'm not sure I have the
What
answer.
is the highest temperature here?
I'm sorry?
What's the highest temperature you're hoping to achieve?
Oh, we want to work in the 1200 range, maybe. Nickel melts at 1450, so we don't go too close to the melting temperature. But then the technology becomes complicated because hydrogen has tendency to leak out. So if you take a container in steel at 600, 700 degrees, the hydrogen can start to leak out.
You can't hold hydrogen.
Right.
It's hard to get.
You can't store it.
It's hard. You can. It's complicated, expensive, and difficult. Okay, that's about it. So if you have questions,
We might do some questions.
yeah, go ahead.
Any questions?
No
Phil?
question.
You?
Okay, yeah.
Have you noticed or have you heard about any gravitational anomalies?
No, we're not seeing because we don't measure it, so we don't know if there is or not. Well, measuring gravitational anomalies is difficult because you are not large effects and you need very sensitive systems. Anything that if you blow on it, it will change the numbers, so you have to be careful about it. Yeah.
Microgravity meters are a little crazy.
It's not easy to do that.
But what you are measuring is output.
Heat.
Heat, yes. We measure heat. And then you have to transform heat into electricity one way or another. But there are many applications we don't need to transform it to electricity. There are many applications for heating. Heating your house, heating
Anything.
the industry. A lot of heat is necessary. Yeah.
I'm not sure this is a question, but Dan has been showing us that
Yes.
structure there.
It's beautiful.
Is there any link between that and what you're talking about?
I don't know because I have no way of seeing what's happening inside my crystal. People are using a lot of imagination. I love it, but it's all imagination.
But if you
don't
had
know.
to say what the geometry of palladium was
Yeah.
at the atomic level, outer electron shell DF, 5/7 spin pair, 1014, dodecikosa, what monatomic means.
I leave it to Dan for that, I am not specialized in that. So,
No, when I see the production of spherical radium, this is a very, very expensive material. We're talking about $1,200 for this amount. And to my mind, this spherical radium had the whole purpose was to get closer to that structure.
I don't know. I'm not the person who knows everything. I don't know if here there are people who know everything, but I don't know everything.
But
But
we
like I
have the
said,
equations to show the radii of hydrogen do nest that way, for sure.
Yeah.
I did prove that, so, which we could stellate and suggest.
But it's possible. But I'm a practical person, I want to measure.
That's why we
If
don't.
it works, it works. I don't care how it works, I find it. When you drink water, you don't care how it works in
No,
your
I
body,
don't
but
drink
you're
water.
happy, your stress is gone,
John Paul is not a theoretical, he is a practical, he's a lab guy.
I want you to measure, I don't care. You take the theory you want that pleases you, that's fine with me.
And we love recording. And we gotta thank John Paul.
Hey,
for being
shut
Hold on, Dan, hold
He came
on.
all the way back.
There's still
from
some
US.
questions, Dan. We've still got time. There's still questions.
Is that
Go ahead, yeah.
Came all the way from America.
I was wondering what other immediate applications would be up your street?
Oh, the first application will be industrial heating things. You have in the industry a lot of people need heat, so that will be the first application. Second will be application maybe to house heating and hot water. Then there will be application of electricity, making electricity, and the last one will be for mobile, like cars, buses, trains, whatever. And last one will be planes and rockets. How about the application for space? In space, actually, not for propulsion, but for energy. I mean, NASA is very interested by going to Mars is a major problem of energy. You need energy. I mean, going to the moon it was only 1 week, so you could use these batteries type thing, But going to Mars, you need a lot of energy. So either you have large panels, it's complicated to do that, or you have cold fusion systems. Maybe you're not familiar, but you have a space probe that go beyond the solar system, and they're still working after 40 years because they have nuclear power plants in it. It's plutonium source. It's a heat source, and they transform the heat into electricity. So they can last forever, kind of. So there's a Mars robot at the moment working on that with that system. but it's plutonium, it's complicated, dangerous, so they prefer, if you have the same thing with cold fusion, it will be much better. So that's another application. Yeah. But it's not tomorrow that your car will be running with that. You can change cars without waiting more.
Can you
well.
say anything about biological transmutation?
Oh, yeah, I could.
That's his field.
That's my field too.
Ah,
My second field.
Yes, yes.
Well, on May 18th, there was in Korea a conference on biological transmutation for nuclear waste remediation. Actually, we are only 4 people working in the world, so it was a small conference. That's not you are so few that you don't need to have a large one. So we are only 4. And but experiments have been done. Okay, the whole thing. I mean, if I start talking about that, we'll need another hour. But anyway, we know that in biology, not only chemistry is happening, but nuclear also is happening. So if you want to have calcium in your body, you should not don't bite stones. You know, it's not good. If you want to have calcium, take silicon, and not glass, but real silicon. There have been experiments showing that the radioactivity of cesium-137 decreases very fast when you in with bacteria. It has been done in Ukraine by a guy called Vysotsky. It has been done also in Japan and Korea also. So now there is a program, an official program in Korea to go to biological transmutation to remove radioactivity. And that's a good start. I mean, there's a lot to do. I mean, it's a big thing, big project. I mean, cold fusion is difficult, but there it's even worse. You know?
But we talked about how central people feel reduced radioactivity.
But
Did you want to mention Louis Kevron?
the camera, yeah, I don't have time to do all
Yeah,
that.
that's
But
right.
it's all story, long story. Yes.
Are there any programs to like proliferate that bacteria? I know like there's also some small things that are breaking down
Radiation.
petrol-based
Yeah,
plastics.
yeah, that's chemistry. There are bacteria that can transform waste into
Are there currently, you said there's just a small group of you, are there currently programs to like really proliferate these bacteria? Or?
Now, the people working in transmutation are very few because you need to do mass analysis, kind of spectrometer to do it. It's complicated. That's very complicated. It's expensive. You don't have the equipment to do that. But we are very few.
But they have proven that it is.
And they're proven.
true.
Yeah. I've made experiments myself for 20 years showing that there is variation in composition of elements when you grow plants.
Do these,
seeds or
do these bacteria have the capability to reproduce based on after consumption of radiation? Or are they able to
I think
sustain themselves?
Yeah, I think they sustain themselves. Yeah, they love it.
Okay.
Otherwise,
That's
they
what we
will
want to
not
hear.
eat it. You know, that's stupid. These bacteria are very smart.
Well, there's a thing with the radio
is it-
couple in Russia that
Any more questions?
Yeah.
We'll talk about
One
that
other
later.
quick question
No, no,
about the
quick
other
question.
thing. So you're hoping to move away from the palladium into more of a nickel-based
Yes.
transmutation. I'm not currently up to date on what the remaining nickel stores are in the planet.
Oh,
Lots,
there
Do
may
you
be.
have that?
lots and
All
lots
same
and
as
lots.
And where are they geographically located?
South in,
Australia,
Luca,
South
Korea,
America, no shortage of
Canada.
people. And we have a question over here. Sandra has a question.
Yeah. That's
Yes, I'm excited to hear you talk about the radiation, biological transmutation, because that's also some of our big focus with the advanced radiation remediation project that I mentioned. So I want to talk to you more about
Okay.
that
You can talk later. Yeah. Okay.
and online with, support. But also and this is for everybody, our technology is designed to create a transmutation quantum effect. It's a superscalar, and so it changes properties of elements. I was working with a professor at School of Mines on a lot of different effects in labs and things like that. I've worked with a lot of different ones. He recently passed. So, but this is an offer for everybody. There's a number of things we can work with, both having different effects in a charged environment within, the EE system that we work with. It creates this superplasma event, etc., with all the phase conjugate wave pairs and implosion. And so there's one thing working within that coherent field. There's another thing, we have another process that hypercharges, like we do the medallions and things like that. And this is where Glenn Ryan's research on this came in and just using a hypercharged medallion. It's crystal, it's toroidal shape, and it's hypercharged. And it was 28% reduction in surface tension of water, 20% increased electrical conductivity, also of the DNA. So there's another process that we can do with taking your palladium, taking the nano, taking different elements, and hypercharging those because of the effect on the hydrogen atom and the different effects that that has as far as superconductivity, and then working with let's enhance anything and everything. And we're also going to be setting up labs, super labs, and so I'd like everybody's contribution on this because there will be massive funding for proper labs. So lists of what we should be doing, and my thing is,
This is up the lab in South France, because we all want to live here.
Hawaii, but they wanted to bring but also we are the combined unified presence that can change the world. We have to come together literally as the greater community, communion of saints, the greater communion, and put our heads together. That's why I said one of my prime focuses here is to create the think tanks, because we have everything to reverse all the issues on this planet quickly.
Thank you.
So
Thanks,
thank you.
Sandra. So we're going to thank you,
Thank
John.
you.
We've got a good break now for half an hour. You'll listen for the bell, and then we've got Glenn Ryan on at 11 o'clock talking about DNA and all sorts
It's
of
past
exciting
11.
things. So have a good little break. Listen for the bell.
At 12.
At 12, sorry.
Not that I think that's right.